Nights beforehand were long, but great for showing up with some warm coffee here. Welcome to session number 13. It's the Emerging Topics 3 session. Again, we have 5 very interesting and diverse presentations in this session. We'll start off with a presentation by Anton Vikotsev from the University of Calgary. So, Anton, the stage is yours. Looking forward to your presentation.
Good morning, everyone. So, for today's talk, I would like to bring your attention to the. For today's talk, I would like to bring to your attention the need for a more detailed lithium-ion battery energy storage model for power system techno-economic studies. Lithium-ion battery storage, it's a fairly new concept in the power system industry, especially if we consider commission projects. And usually when we do techno-economic analysis, we employ very simple energy reservoir model. So it's basically energy comes in, energy comes out. And if we consider degradation, most of the times it's empirical formulations. And so we use this model in our techno-economic analysis. And I was sure that what we are getting, so basically we are getting dispatch for the energy lithium-ion battery energy storage. Is it feasible schedule? So will it violate the constraints, like physical constraint of the lithium-ion battery energy storage? Okay, are the economic benefits accurate? Can we rely on this like dispatch? And I'm not sure about this. And I'm not sure of this because, in fact, battery energy storage is a more complicated system. It consists of battery management system, power conversion system, thermal management system, and a lot of hearts of this unit is lithium-ion cells. And in this talk, I will show you that, if we can advance, at least in more advanced modeling of at least each one of these units, it can be better. We can get a better model for our optimization framework for our economics and economic studies. So let's talk about lithium-ion cells and how we can model them. So this one again. So this is the simple one to the left. It's our usual energy reservoir model. So it's linear model, and this is why it's so popular. People use it in the optimization framework for different optimization frameworks. And there is a more advanced model, which based on the physics, what's happening inside, under the hood of this lithium-ion battery storage, and basically under the hood of the cell. It's a physics-based model, and there is different physics-based model. But in general, they are nonlinear, and if we model them, we usually use partial differential equation, order differential equations. So let's talk about the simplest from the physics-based lithium-ion cell model. It's single particle model. So what we have, it's a single particle. We can consider this model kind of as a cabbage. So for the external layer, it's our power, and power we need it's our market variable. It's for our market model. Then next layer is a current and voltage. So we apply current through the cell, and the response of the cell will be voltage. The next layer? It's what is happening inside. So for the lithium-ion, for single particle model, it's simplest electrochemical model. Basically, so this is our lithium-ion cell. Each electrode consists of electrode material, and usually it's like electrode particles, small electrode particles. And with single particle model, we assume that all particles are the same, and basically we model the whole electrode as one spherical particle. And the voltage response of the system mostly depends on for this model, and for in case of low current it depends on the transport of lithium ions inside inside of the electrode particles, inside of solid electrode. So it's equation 4 with the corresponding boundary condition. Then electrochemical reaction on the surface. It's equation 7, which is described by Boltzmann-Volmer equation, which needs like equation 8, which describes if there is no current through the cell, still there is equilibrium processes, some ions coming from like leaving electrode, some entering electrode. Then parameter, open circuit potential, basically parameter, it's measurable, so it's parameter, and it shows the potential of each electrode, depends on the concentration of lithium ions inside this, each electrode. And using so we can calculate equation 10, it's our solid electrolyte potential, which consists of this open circuit potential plus over potential, which comes from the, when we have current through the cell, it's either increase or decrease this open circuit potential. And the difference of this, the difference of these solid potentials will give you the voltage of the cell, so voltage across the cell. And to link together the flux of lithium ions through the surface of this electrode and the internal current, it's so equation 12, which shows the flux of lithium ions. So you can see here it's like partial differential equations, nonlinear equations, hyperbolic sign, some radicals, and other nonlinear expressions. So it's very difficult to incorporate this into the optimization framework, like which we can solve with traditional solvers, like linear or mixed integer linear. So what I did in this work, we tried to linearize our model. So here I brought just for so two models which I will compare in this study. So one of them, it's simple energy reservoir model to the left, and the other model is our linearized physics-based model. So what problems we have? First, we have to linearize our power, because power products current time voltage, and it's like variables of our system. So this is the method how we linearize it. Then we there is for our partial differential equations, we can find our approximated solution using this system of algebraic expression and ordinary differential equation. And then this is expression for the over potential, which was we get by simplifying Butler-Volmer equation. And this is like it's this one open circuit potential as function of the applied as function of the surface density of lithium ions. We approximated using piecewise linear function. And so this, and now it's our to the left and to the right is both mixed integer linear problems. So this one is like, let's look at apply this model, incorporate in the simple energy reservoir model for one day. And this is our, to the right is our price profile. This is our parameters, so we can see the LG. So we can see the, like, let's assume that our imaginary lithium-ion battery storage is made of LG50 lithium-ion cells, which is like, it's made, like the main parameters for us is the chemistry of electrode, it's carbon and nickel, manganese, cobalt electrodes for the positive electrode. So here, so basically, we consider 10,000 cells, construct the lithium-ion battery energy storage with this capacity and power and charging, discharging power. So when we solve this problem, so this is what we can see, that of course we have more constraints, so the number of constraints has increased, number of binary variables has increased, and time to solve, like it's significantly increased. But what what was the results for this model? The results were that you can compare here. So energy reservoir model and the linearized physics-based model. So let's start from the beginning. So at hour 3, the prices, there is the highest price. And battery was, we assume that is fully charged, was fully charged at the beginning. So the energy reservoir model wants to discharge completely because it's the highest energy, like it's the highest price in the first hours. So it's discharged in hour 3. Compared to the model, linearized physics-based model, it's physically impossible, like because of constraint on the, which arise from the lithium-ion cell, to discharge all the capacity within this 1 hour. So in this case, we do it in the we discharge in the 2 hours. So this similar, it's in hour 21 here and hour 21 here. So the prices again was high here. So the battery energy reservoir model wants to discharge immediately, like not immediately, but within this hour with the highest price. And for linearized physics-based model, it's discharge the battery within 2 hours. Next, what I want to bring to your attention is that when we charging the battery and charging the battery and discharging the battery here. So here the prices at hour 6, they're almost close to each other, right, over there. So in the reservoir model is discharged at the low, charge the battery at the low price. But for linearized physics-based model, it's models the efficiency of the lithium-ion cell. It says that it's not, efficiency goes, decreases when we charge the battery at higher power. So when prices are almost the same, it's beneficial charge and discharge, like compare this one, hour 12, within several hours. It's because of efficiency consideration. And physics-based model consider efficiency. It changes with charging, discharging power and state of charge.
4 minutes left.
And for energy reservoir model, efficiency is constant. So next, we consider 1 week of operation. And for 1 week of operation, so this was done with real prices from Alberta electricity market. They hit, so we run our models, energy reservoir and single linearized physics-based model. And now we want to understand what we get are these correct results or not, because all at the end of the day, they're both approximations of the real model. So we built a digital twin. So digital twin means like we constructed the simulation, our simulation model, careful without any approximations, and bring the dispatch from each model to this simulation. So, and it's, we get there that for a reservoir model, in 20% of time instances when the battery was either charging or discharging, there was violation. And for the same criteria of violations, we have just 4%, around 5% for the linearized physics-based model. So, and it's first one. And second one, when we, what is the observed profit? Basically, our digital twin corrected our dispatch, and still, with a linearized physics-based model, we get more profit. Okay, next. Next, I want to talk quickly what we are doing right now. So it's linear physics-based model can be easily linked to link with a physics-based degradation model. And again, now we use linear degradation model, which is good for our modeling. But it's our degradation is empirical, so empirical based. So it's better to use physics-based degradation. Problems, it's partial differential, ordinary differential equation, non-linear. So what models we use in the power system economic studies? So linear model, energy throughput method. So it's just proportional to our discharge energy. so our degradation.
2 minutes left.
Next method is a rainflow algorithm. So it's a more advanced method, and we're looking, so degradation is proportional to the depth of discharge. So we know that it in theory should be a higher, and to practice higher depth of discharge will lead to greater degradation. And for this particular talk, we can consider physics-based degradation, and one of the degradation mechanisms. There is another one, it's like several. The simplest one and the biggest contributor to the aging of a lithium-ion cell is growth of the solid electrolyte interface. And this is, degradation is proportional to basically this contribution from this side reaction. And okay, so we have simple energy reservoir model to the left, physics-based to the right. And then from physics-based, we can build this, calculate this current density of this side reaction for solid electrolyte interface. It was difficult even this model to solve even without adding description of this growth of the solid electrolyte interface. So in order to simplify it, we link together two models, energy reservoir model and linearized physics-based model. And what we did, basically, in the linearized physics-based model, we get rid of the, so before we model power as product of current and voltage. So we assume that our voltage, if we fix the voltage, we can link together these two models. Okay, so when I did this, and I compared for case study, again, it's energy arbitrage problem for 1 week, Alberta electricity prices. So I consider no degradation, energy throughput method, rain flow counting algorithm, and proposed hybrid physics-aware degradation model. And degradation, I can, again, so when I ran the model, I got the dispatch, I then use my digital twin to calculate a real degradation. So it's last line. The first line is our profit over 1 week. We can see that all the models, the profit decreased like from 7 to 5% when we consider in our objective the cost of degradation. But when we consider, when we look at how much we degrade the battery, so the proposed physics-aware degradation model provide almost 40% less degradation than case without degradation, like the first column. So it's significant difference. And conclusion, yeah, so we propose a linearized physics-based model. Also, we propose a hybrid model for degradation studies. We can see that this model leads to a lower capacity loss, and for future development, we should consider more detailed linearized model, or more like other linearization techniques, like to get rid of this, like to decrease the number of violations, and consider more complicated market structure, maybe several market products.
Okay, great. Anton, thanks for your very interesting presentation. We have time for one very quick, Claudio, please.
Claudio Canizares, University of Waterloo. Interesting work. You demonstrate that this model really makes a difference in your economic analysis. However, can you comment on the number of parameters you require and how to obtain them to make sure that this really represents the battery you're dealing with? Because I found that quite complicated and might be worth it, but how do you obtain them then?
Parameters are measured, so there is, what I see now, there is a little bit disconnect between lithium cell community, people who develop the cells and who optimize the cell, what will be the future cells and lithium-ion cells, and power system community. So they use different models. So in lithium-ion cell community, for different electrode chemistries, they have like for certain cells, they measured the parameters of the cell, which I can use in my model. Of course, from the, if we consider, like we are buying some ready product from Tesla or from Saft or from cattle, we don't, sometimes they put what is the chemistry was used. If they tell this what chemistry we use, we can extract, we can get these parameters. Because this, for example, open circuit potential is known function. It's like for the voltage of the chemistry depends on the concentration of lithium ions on the circuit. Parameters of the cell is not so good. So like geometric parameters. Sometimes there is, for example, for this LG cell, there is available data. There is data for some LFP electrodes and for some cells with LFP chemistry, but not for all.
Okay, let's leave it at that. Thanks. There will be more time in the discussion round to go into more details. So now we are coming to our second from Ilgiz Mutsakanov from DTU on neural networks and OPFs. Yeah, sure.
Okay, thank you for introduction. So I will present our work on neural networks for encoding dynamic security constraints, optimal power flow. Before I start, I would like to acknowledge my co-authors, Andres, Yogis, and Spiros. So this batch of power systems should comply with the static and dynamic security criteria. In some works, ACOPF is seen as a solution for determining this dispatch. So let's look closer to this ACOPF problem with static and N-1 security criteria. As it follows from its name, we optimize some objective. In our case, we took minimizing of active power generation for the intact system state. This problem is minimized with respect to constraints. So these are pretty standard constraints of upper and lower limits on active and reactive power generation and voltage limits. Then there are also constraints on the apparent power limit in the lines and nodal balance in the nodes. So note that all these constraints should be satisfied for all contingencies. In our work, these contingencies are line outages. Finally, we follow this preventive control scheme when, no matter what contingency, our active power generation and voltage on generation nodes should be the same as for the intact system state. So this setup looks good. However, it doesn't consider for dynamic security criteria. So since it's required for the dispatch, one of the examples of such dynamic security criteria is small signal stability. We would like to include it. And such constraint would be limiting the damping ratio. So in our work, we consider that the damping ratio should be greater than 3%. However, there are two problems once we would like to include these constraints. First of all, there is no way that we can directly put this constraint into the ACOPF problem. Second, adding this constraint itself makes the problem intractable. Further, we propose an exact transformation to encode dynamic security constraints in OPF through neural network. So why we think that neural network can handle this kind of problem? Because AI has the ability to determine complex relations in a very short time. So there was a problem which was not solved for 50 years by the scientists on this protein folding. And then just in 2020, a solution from DeepMind solved this problem in several hours with the accuracy of 90%. So being inspired by this example, we would like to look on our problem and discuss the training of the neural network. So we train a classification neural network, and we provide active power generation and voltage on generation nodes for the intact system state as input to our neural network. Then the neural network trains, and it outputs if the provided operation point is either feasible or infeasible. So basically, it evaluates this, our input. And I would like to demonstrate this on this figure. So here, each point is an operation point, and the red points are the ones which are infeasible, and the blue ones are the feasible points. More specifically, in our neural network, we encode it as if Z1 greater or equal than Z2, then it's seen as feasible, otherwise it's infeasible. So we will use this notation also later. In our neural network, we use ReLU activation function. This is how it looks. So if input to this neuron is negative, it will output 0. If it's positive, it will output the input itself. So by introducing one binary variable per each neuron in the hidden layers, we reformulate this ReLU activation function in the mixed integer problem form. So summing up, what we did, we had a neural network, and we introduced it in the form of MILP with linear weights and ReLU transformation. Also, during training, we gradually increased the enforced sparsity of the weight matrices to 50%, which means that 50% of entries of the weight matrix W was 0. That greatly increased the tractability of the resulting MILP. So now, comparing with our original problem, we are just left with the objective and these three constraints. And then all the small signal stability constraints now are in the forms of mixed integer constraints from the neural network reformulation. And the last constraint just ensures that our output is feasible. So in this formulation, we only can make it better by keeping in mind that this is a nonlinear constraint. So the nonlinearity comes from the loss term, and we propose this iterative linear approximation by the first-order Taylor expansion around some known operation point. Then we just replace that nonlinear constraint with this reformulation and solve this problem. So if at this point you're still skeptic that neural networks could resolve this kind of complex problem, then you're right. So for some applications, getting 99% of correct classification would be okay, but that's not the case for power system and also like for other examples like these autopilot cars. So in this case, we would like to be feasible in 100% or safe, even that comes at the cost of some suboptimality. So we address this problem by introducing the conservative parameter. I will explain this with this figure. So this gray region is true feasible space. And then, as I explained earlier, this is points which were evaluated by the neural network. The red points are infeasible, and then blue points are feasible. Then if you just look closer to this, you can determine there is a feasibility boundary between these two. And basically, our formulation would say that anything inside this boundary is safe, but that's not the case. So there are some points which were wrongly classified as stable when they are not in fact. And this is exactly the type of problem we would like to avoid, this false positive, when we think that we are feasible or safe while we're not. So we address this problem by introducing this conservative parameter epsilon, which effectively shrinks this region of predicted feasible points so that all the points inside this region are truly feasible. Some details on the setup. We use 14-bus system. We work with a data set of 45,000, which is has equal number of feasible and infeasible samples. And then we follow some classical approach on the splitting training and test data set in the ratio 80:20. We use 3 hidden layers with 50 neurons. That was enough for our setup. And then we evaluate the performance of our methodology for 125 random functions that allows us to better capture different parts of the feasible region. So we Next, I would like to explain the different problem formulations that we have tested. They have different type and result in different generation costs and percentage of feasible solutions. So please note here that this percentage refers to the problem with static n-1 and small signal stability security constraints. So if we look, ACOPF just gets more than a little bit more than a third of all, just a third of solutions obtained by ACOPF are feasible with respect to these constraints. Next, by adding up n-1 security, we obtain the same share of feasible solutions because the violated constraints in both cases were small signal stability constraints. That increases slightly the generation cost, and then we add up the small signal stability constraint that increases our percentage of feasible solutions, and that comes at the cost of some generation cost increase, which is expected. And then we experiment with this conservative parameter epsilon, and then for epsilon equal to 8, we obtain that all solutions provided by this formulation are feasible. So the interesting part here, I would like to look at this epsilon equal 8 and 0. Here we can see that it was worth this kind of trade-off of conservativeness for the purpose of feasibility and the cost, because the difference between these two is less than 1%, while the feasible solutions increase just almost like twice between them. Okay, here I would like to show more the change of the cost function and the percentage of feasible solutions for different values of epsilon. And here it's obvious that the objective increases linearly, while the percentage increase in these kind of jumps. And the most interesting point is here is between when epsilon transition from 7 to 8. So there is a very small increase in the cost, while the share of the feasible solutions increase from 84 to 100%. Yes, so in this work, to sum up, we capture previously intractable constraints through neural networks and exact reformulation to MILP. Also, I think I demonstrated how the proposed approach allows obtaining cost-optimal solutions, which are at the same time satisfy both static and dynamic security constraints. And also, our solution ensure the feasibility by introducing this type of epsilon conservative. That is all of my presentation. Thank you for attention.
So again, there's time for 1 or 2 questions that immediately follow up the Irgit's presentation. Yeah, Patrick?
Yes, Patrick Concierti for Research France. Yes, thank you for this very interesting work. Just to be sure, did you sample the availability of the generators on the line in this study or not? You are just sampling the load and the...
Yes.
What are you sampling?
So it's basically the set points, which are active power generator set points, and the voltage magnitude.
Okay, so you are not sampling the generation unit are all the same all the time? Just the active power that is changing?
Yes, and voltage set points also.
Okay, but the number of generators are all the same?
Yeah, the number of generations remain the same.
Okay, thank you.
Okay, then thanks again.
Is it open? No. So this gets us to the next presentation. I just want to say, I don't know whose idea was actually that Andres and I are together during the session, but we did our pieces together. We started with 1 month difference, and our first conference together was IREP, actually, 2010.
Yeah,
so
back in Rio.
Yeah, and we wouldn't have thought that 12 years later we would actually be chairing this session together after being our first over here. Vladen.
Thank you.
All right. Forward, backward. All right. Thank you. Good morning. So here's the topic I may have to stand on a side to see what's happening here. If we could just put it with the slides. So this is the work done by my graduate students, Rashid and Mohammed. And they did different things that I will talk about. And then in this paper, these things came together for a good reason. So that's kind of interesting. But before we go there and tell you what we did, I want to kind of summarize here what the purpose of the paper is. The title is very broad, but I would like to bring your attention to three things. One is prediction of the state of risk. You will see what the risk is. Risk is risk of outages. So prediction of outages formulated in terms of the risk. Then the mitigation is the second point. How do we mitigate? And the third point about the net zero carbon electric grid is that we would mitigate that with a flexible load or virtual power plant or whatever you want to call it. So that's the point of this presentation. A lot of things here that I will go over quickly. The problem statement is at the top. How do we use the distributed energy resource flexibility to reduce the carbon emission given the state of risk constraints? So that will be the emphasis. And there's a little bit of a discussion of all of that there. We are focusing on participation of DERs, or flexible load, in the wholesale market in this paper. So we are helping with this the aggregators. Even though the DERs, as you know, are connected to the grid and can offer service to the utility company, distribution company, but the resource is flexible, so the resource can be connected to the distribution company, but offer services that are actually helping the aggregator to procure ancillary service products. So that's what we're going to talk about. Now, you all know this. I don't need to talk about this much. Don't worry about these estimates, whether capacity is exactly what you see there or the cost is exactly what it is. The point is, it is feasible today, it is affordable today to a lot of people to have what we call a nanogrid. We just call it nanogrid, I guess it's a term that we used. And that is to have the PV, to have the stationary battery, and to have mobile battery in the form of the electrical vehicle. Remember, it's mobile, so it can go in and out. I, have little notes from last night checking the website. In Texas, where I come from, Tesla has opened a gigafactory, as you know, in April, and they are just pushing things out. 125,000 power walls, stationary batteries per year, 150 electrical vehicles per month in each of the major towns, Houston, Austin, and so on. Solar is already there. So it's only a matter of incentive for you and me to invest that money up there and get the backup for our own load and participate in the services with the distribution company and be paid, and participate in the ancillary services through the aggregator and be paid. So the technology, we don't see an issue there. We just see the issue of regulation, of how all of this is done, and realization of the utility companies that they can benefit from the flexible load through the services for their own function, which is the reliability function, that if they don't stand for that, they're going to lose money. And so paying out to be reliable makes sense. It's actually earning money, if you will, by paying out, in a sense. So that's our thinking here. You all know about, well, I shouldn't say you all know, but there's a FERC order 2222. It did order, it did order actually aggregators to be permitted to participate in the wholesale market. Texas is interesting. For those of you that don't know much about what's happening there, you may read, annual reports of our, or I should say biannual, because our legislature is every other year. You can read the reports. The aggregators were only allowed in Texas to aggregate load for load management for efficiency purposes, and they were paid for that. They were not allowed to participate in the wholesale market. So now they are. Now, this is the key diagram. It's kind of a general, but I'll try to guide you through this. And as I guide you through this, please look at the clockwise direction of this diagram. It has to do with the prediction of the state of risk. So we start with the weather, and everybody talks about weather. You will see how granular we are in what we do with weather. You start with weather, you define something as, that is called a hazard, which is basically probability of the weather causing problems. Then you go down into the grid and you define a conditional probability that that weather condition at that time will cause certain problem in the grid. We call that vulnerability. And then you multiply all of this and you get the prediction of risk, which is spatial and temporal, very granular in both directions. And then you talk about management and mitigation. Again, this is the definition. I just explained what it is. The economic impact over there depends on what you are trying to mitigate when you have the prediction of risk. This is the framework that we use. Now, you see there utility, nanogrid, and aggregator, and state of risk is calculated by the people that have information that can produce the state of risk prediction, and it's shared with the load, with the flexible load and grids. That's what's happening right now as we speak, because since 2013 at the IREP in Brazil, in Búzios, we were focusing on this. We moved this prediction into an investor-owned utility for several years, 5 years, before it got implemented. We moved it later on to a co-op. We're now moving it to a muni. It's working, and the assumption of these examples is that they will share state of risk with the flexible load in this case. And then the aggregator shares whatever it needs to share with the people that they aggregate. Just to give you a flavor, on the left-hand side is what may cause outages. On the right-hand side are the databases that you are dealing with to actually identify the causes. And there are plenty of different databases out there. Unfortunately, or fortunately, however you want to look at it, you have to integrate them in a particular way. It's not an easy job. That's why it took us 5 years to implement it in one place, but once you learn, it's shorter in the other place. The weather. We all talk, well, hell, we all been aware of the weather, but be aware the weather comes from all kinds of sources. It's not something that is one weather parameter. It's many, many different weather parameters coming from weather stations, radar, satellites, and so on. They are typically readily available, free of charge, typically. The next thing here is, for example, the vegetation information. You can get any parameter you want about the trees, at least in Texas. In every corridor, every single tree, you know what species it is, and with certain LiDAR stuff, you know exactly what the height of that is. Knowing the weather parameters, you know how quickly it grows and so on. So you can really predict well what's happening with the vegetation. You have to go to a number of databases. And then the complexity, of course, comes, because what are you predicting? Things can fail on the generation side. Things can fail on the distribution side, on the transmission side, and so on. So it gets a little bit complicated at one point in time, but it depends what you want to do with it. So this is the example of what we are using as an input to this problem of optimizing the use of the flexible load for the aggregation purposes. So please follow the left-hand side. The first map there is the weather hazard map. Developed very granularly. You don't see that except in the middle where that corner shows. It shows every feeder, every lateral on the map, the risk map. So you have that weather hazard. You move into vulnerability in the middle. That's the map of conditional probability where the issues can pop up under these weather conditions. You multiply the two and you get the risk map. That, with a little black there, is the risk map. So low risk up there, high risk down there. Optimization is to introduce mitigation measures. That's the one in the middle here with the black. You can do certain things to eliminate. This is prediction. So you have the time to do the mitigation and plan the mitigation. And once you do that, then you can do these other things. So now let's move on. So what do we have? We have this flexible load, the nanogrid, and we have this state of risk that is available. So what the aggregator needs to know is if the aggregator bids in the day ahead, hour ahead, and so on, it needs to know what is available in terms of the resource at that particular nanogrid, not necessarily what the nanogrid has originally perhaps committed, but what will be available when needed. Because that's the aggregator's problem. How to hedge this risk of things not being there. Because they're going to be penalized if they procure the service and they are not able to deliver. So that's where we step in with this. Now this is a little bit confusing if the net load minus PV, meaning really PV minus load is negative or whatever. But however you want to do it, is at one point in time, under this condition, where the ancillary service may be needed, there may be outages in the grid because the problem is occurring for hours in a given region. So this here is considering if the load, this flexible load, nanogrid, gets disconnected, there's a probability that it will get disconnected, what it will do. It will first deal with its own load, obviously, with its own generation. Will start to get the batteries up immediately, because this is prediction, both on the vehicles so that they can move, and then the stationary battery. There may be spillover of the PV, depending what they do then, because they are disconnected from the grid now, okay? And they are also managing the load, its own load, deferrable load, the critical load, and, okay. So after all of that is done by them, what the aggregator sees now is actually, this is an example of 10 feeders. So the colors are the feeders. Each feeder has about 50 of these nanogrids. And this is what is happening hourly with the resource. So the aggregator now receives this information before bidding. And it's very near-term information because this may be provided this morning and they may bid before the end of the day. So they are receiving this. This is just showing how the ramp up, ramp down would change depending on what's happening in the nanogrid. And there's also the repair time that plays into this. In other words, if the flexible load is out of service, how long it's going to be out of service, because that determines all of this depletion of the resource on its own load. And you may or may not know this, but actually the historical data that is used for machine learning here does provide not only the information about past outages, but also about the duration of the outages, because they are responsible for reporting SAIDI, and other indices that include the interruption times. So based on the interruption times, they can project how quickly they can get back to the grid. One last thing to clarify is this, and the reviewers came back with a comment that I think was a little bit of a confusion perhaps on our side, how we presented the things. You know, the question we received from a reviewer was, well, you know, flexible load is going to take care of itself first before anything else if there's an outage. Well, if there's an outage, there's nothing else to do. You cannot participate in any service. You are disconnected. So all you can do is to worry about your own load. The issue is when you come back, are you ready to offer all of the capacity or flexibility to the aggregator? And the aggregator needs to know that because they want to use you at one point in time very quickly. And you may not have the resource that you used to have before the event has occurred. So I hope I communicated the basic idea of what's going on here. The paper gives more. There are some other papers talking about this and so on. So I would be glad to entertain any questions at this time. I hope I didn't go over.
Great. Yeah, Johan, questions?
Jochen Stiasny from Technical University of Denmark. So I would be interested in the state of risk. How do you, in a sense, validate that? Because you only get one realization reality afterwards. How do you validate your state of risk estimation?
You know, it's a little bit not quite, you know, right to say this, but it's simple. And why it's simple? You take this historical data. First of all, you have to have access to data. Okay, so that's one issue. We, in our case, we don't have problem with access to data because we just contract with the utility company, and utility company, under non-disclosure agreements, opens up all of the data that they have and basically say, whatever you want, we'll give you, but give me that outcome. So, you know, we get the data. That gives you the history of what was happening in the grid. So what you can do is this. You can take data from, I don't know, last 10 years and project with this method in 2020 and see what this prediction says for 2020. They know what has happened in 2020. And then you can also predict in 2021. And so your verification is how much are you off? And so verification is not a major problem. Now, don't get me wrong. This is not something that, you know, is easy to convince people to do and all of that. And the accuracies are expressed as percentages of this risk probability and so on. So there's a lot of stuff going on there. But in general, to get the notion that this may work is not too difficult. So we were able to convince, based on this approach, 3 major types of utilities in Texas. You know, major types are investor-owned, munis and co-ops. And these are independent people. You know, they have different clientele, they have different way of thinking and all of that, and they all agree to fund independently this activity. So I don't know if this helps.
Great. Thank you very much, Mladen. One round of applause. Sue is going to present.
Okay. Yeah, thanks, Barry, for the introduction. I'm Bolan, I'm in Columbia, and this is the work with my students, Nick, who is currently doing intern at Argonne, and this talk will be talk about comparing market model for energy storage in wholesale markets. Okay, so I guess the motivation here is we're seeing a surge of storage capacity in U.S. power system. Now, this is a report from BTU Analytics, and they say that, you know, in 2020, so the storage in California was somewhere around 200 megawatt, and now it has reached, in this report, it reached 1.5, and now in CAISO, I think there are 3,500 megawatt storage, and the CAISO is expected to reach 12 gigawatt in 2025. That's in another 2.5 years. So this is California. Then another market is seeing surge. It's ERCOT. It has more than 1,000 megawatt storage already, and there's a lot of deployment over there. Okay. So let's look at the markets. So we are talking about storage participating in transmission grid services and in deregulated power systems. We need to go to do this through market, and we have 3 major groups of market storage can participate. The first is frequency regulation, or broader concept is ancillary service market. This market is actually still one of the most profitable for storage, but also has a relatively small capacity, right? California's frequency regulation is somewhere around 300 megawatt, where the storage capacity is 3,000, so it's already more than the market capacity. The other is the day-ahead markets, which actually transacts the majority of the energy transaction in power systems. So we have a relatively good knowledge about how to put battery in day-ahead market because it's the 24-hour optimization. So you basically model battery constraint there, solve a 24-hour optimization. But the profit revenue in day-ahead markets are not as good. As you can imagine, the battery, the arbitrage price differences, so you would expect a more volatile market, but in day-ahead market, the prices are more stable. Okay. So that leads us to the third option, which is the focus of the talk today, is a real-time market, which still has pretty volatile prices. The profit is still relatively good for storage. But the challenge here is how do we incorporate battery into real-time markets. So that leads to the outline of today's talk. We'll first introduce a new market model for bidding model for battery, in which the base depends on state of charge. Then we introduce algorithm to generate bids for this model, and then by combining the market model with the bid generation algorithm, we compare existing and the new model in a price taker simulation, and we compare the market revenue to represent the utilization of the storage. Okay. So currently, in most ISOs, they dispatch storage in real-time markets using bids instead of physical parameters. Of course, they still need some hard constraints like power rating, but they will not optimize storage state of charge in that sense. And the reason is most real-time dispatch consider only single time period or with like 1 hour look ahead. These periods are too short to model the state of charge evolution, so usually that will require like a 24-hour look ahead. So instead, system operator has allowed storage to do price prediction and design bids to maximize their own profit and submit to the market, and the system operator can only check the bids. Well, if the price is higher than the discharge bid, they discharge the battery, and if the price is lower than the charge bid, they charge the battery. And this is a pretty nice figure from the work by Warren Powell, which is one of the first work in this field. So here, this will be basically this traditional model in which the storage only submit 1 bid for charge and 1 bid for discharge. The other model we are introducing here is an SOC-based bidding model, which is currently being proposed in CAISO. So in this case, the bids depends on the state of charge, and this is actually very similar to generator, in which bids depends on the the power rating, right? To model the piecewise linear Hillary curve. So in this example, the battery submit 1 base to charge, meaning whenever the price is below $20, the battery would like to charge until full. But in terms of discharge, the battery is willing to discharge to 80% or 80 megawatt hour if the price is about 45. And then if the price is higher than 60, the battery would discharge to 15 megawatt hour. And if the price at 100, the battery will be willing to discharge until empty. So in this case, the charge and discharge bids or the decision is dependent on the battery state of charge. Now, why do we want to have a state of charge dependent model? And there are actually 2 motivations. The one is the physical reason. That actually, I think Anton's talk, the first talk by Anton actually gave a pretty good summary that battery is actually a pretty complicated device, and a lot of the parameter, degradation rate, efficiency, and power rating are dependent on the state of charge. So there's actually a physical motivation here. On the other hand, if you look at economic, there's actually a motivation to model state of charge, because if you look at the opportunity cost, and in this figure, the marginal opportunity cost of state of charge is also dependent on the state of charge itself. And here it shows it is a monotonic decreasing trend, meaning the more energy you store in the battery, the less valuable they are. And this actually follows the diminishing rule of economics. It's like your bank account, right? The more money you have, the less marginal value that money is. And this actually also follows the requirement by FERC Order 841 that requires system operator to better monitor physical and economic characteristic of storage in the markets. But the scope of this study is we won't look into the nonlinear battery yet, but we are focusing on looking at a linear battery model and how a state of charge dependent bidding model would improve the battery revenue in markets. Okay. So this is the model of the dispatch, but then the more critical question, or the more difficult question here, is how do we generate the bids? Because we're not dispatching storage using physical parameter, but based on the bid to generate. So we use a dynamic programming framework to generate the bids, and this is actually also here a pretty simple, kind of a minimalist formulation of price arbitrage, but in dynamic programming, So you can see this where it starts the recursion, the recursive definition where the value function is defined as they maximize the profit, and it's dependent on the energy stored at the beginning of the time period. And then at each time period, the battery maximizes the market income, so the price times the difference between charge and discharge power. The cost, the discharge cost in here, we represent the cost of degradation, the linear cost of degradation, and the value function, which represents the maximized profit over the next time period. So basically, the battery just trade off every time period based on how much money it can make now versus how much money it can make afterwards based on the energy stored in the battery. Okay, and it's recursively solve it. Of course, then you go backwards and resolve it, and then you have we have the physical constraints and models, the power rating, energy rating, and the inefficiencies. Okay. So how do we move from dynamic programming to BIS? So it's actually the value function. There's actually a pretty nice way to do this. So we look at the formulation. We have the revenue part, right? And this comes from the market. And here is the cost part. It's a single period cost part because it's already formulated as a recursive dynamic programming, which consists of the physical cost and the opportunity cost, right? And then we design the Baiting curve. We want to get the marginal cost. So basically, we take the derivative of this guy with respect to the battery power. And then we use the state of charge constraint to get the derivative of the state of charge versus power. And we put everything together. We get the discharge cost curve and the charge cost curve. And this, you can also consider this as one of the mathematical proof that shows that the cost curve is dependent on the battery state of charge, which is a E here. Okay, so if we get the Q, we get or actually the small q, which is a derivative of the big Q, we get the BIS. And then the question is, how do we calculate the Q? Okay, so there is a lot of approaches on solving dynamic programming for battery, but here, targeting this kind of very simplistic arbitrage formulation, so we figure out that it all goes all the way back to my my days back in MIT, that we did this work with Aldun and Magnus, that we find an analytical algorithm to calculate the value function. So this is a kind of an ugly equation, mainly to deal with the constraints, lower and upper energy constraints. But if you look inside the formulation, you see that all the parameters here are known. Okay, so we have the price, efficiency, power rating, and discharge cost. The only variable here is the E, but E is used as an input, more like an inquiry point. So what we do is we basically sample this to get a piecewise linearization, and then we go back in time and solve it. So basically solving a dynamic programming using brute force. And the reason we can't do this is we only have one state. So we don't have an explosion of state complexities. So that's how we make this possible. And this actually solves pretty fast. In a couple of milliseconds, you solve it. And so this is the idea that we get the price predictions, we put it into a dynamic program with our physical parameters, we generate the value function curve, and based on the value function curve, we design the charge, the 1 segment BIS or the 5 segment BIS, okay? And these BIS are also time dependent. This is just one example that we have the real-time price, and then we assume perfect price forecast and generate the BIS based on this real-time price. And this is the BIS, red for the orange for the charge bit, blue for the discharge bit, and they are more kind of follows the kind of looking very similar to moving average of the real-time price. Here they have hourly resolution because we assume the storage can only update the BIS every hour. On the other hand, if you go to 24-hour battery, that this will consider a long-duration battery, the BIS start to get pretty flat, almost like constant throughout the day. So, yeah. Okay, so based on this, what we do is we assume a price forecast. We generate the BIS. We put the BIS into a arbitrage simulator, and then using the price data, and here we use the New York City price data from 2019, the full year, and to simulate based on the forecast and the market model, how much revenue we can get, okay? So here we normalize everything to 100%, and here different storage durations. And it turns out here with the piecewise, with the state-of-chart segment model, here we use 10 segments. It actually gets almost 100% profit compared to a perfect foresight arbitrage. And here we're assuming, again, here we want to compare the model, so we assume perfect price forecast, okay? But if we go down to one segment, this is the existing storage market model, our profit ratio reaches somewhere around 95 or 90%. So here we're looking at somewhere around 5 to 10% of the profit loss only because the market model, the market design, okay? The market design lost 5 to 10% profit, okay? And then this is assuming perfect forecast. The next comparison, we assume a day-ahead forecast. So in this case, we use a very naive approach. We take the day-ahead price and use it as a forecast for real-time price. In this case, we see that here the storage duration is starting to make a quite significant impact. So with short duration storage, if you use a very naive day-ahead forecast, you only get somewhere around 80 to 50% profit. But as the storage duration goes up, you can actually get away with a relatively naive forecast, which means a longer duration battery is easier to operate, okay? And then just to compare, we also tested arbitrage using day-ahead price, and here it's because the day-ahead price are less volatile, so we also want to show how that impacts the battery. And it also shows somewhere around actually 10% improvement or the profit with the SOC dependent bits, okay? So the conclusion is actually pretty straightforward. We tested the SOC segment model, and it shows that it's actually improved the profit by 5 to 10% compared to existing single segment, existing market model, basically in perfect forecast or in imperfect forecast. And we are doing actually quite a few current work on incorporating this model. This is the price taker study, but we are doing some price influencer studies. We incorporate stochastic price models and also nonlinear storage model into the test. And if you're interested, we actually have some new results in my website. Okay, thank you.
Questions? Yeah. Ian.
Ian Hiskins, University of Michigan. These questions may relate to future work. The first one is, you're assuming price taker, right? That you're not influencing the price. But if you've got a gazillion people with batteries who are all looking at price forecast and all acting on that same price forecast, they're going to make decisions which are going to influence the price forecast. And so you'll get a synchronization happening. So that's one question about how to deal with that. And then the other question was, again, if you've got a gazillion batteries doing their thing, eventually there will be no price difference, right? There'll be no opportunity for arbitrage because everyone, when there's solar or whatever, will be charging and the price separation will flatten. And so the more battery storage schemes that you have on the system, they're going to drive them. As you add more, everyone will go bankrupt. Does that make sense?
Yeah. Yeah, so thanks for the question, Ian. Yeah, actually, that's a very good point, and I actually have one backup slide directly to this. Actually, I think it's more related to your first point that, yeah, all the batteries are predicting prices and design bids, and California ISO actually recognized that. It's saying, well, battery bids should depend on the highest price prediction to capture their opportunity cost. And also, they actually show the data that the battery bids are kind of volatile also, and they kind of a synergist with the prices. So I think how to understand this, especially in incorporating a price influence or price maker model, that will be definitely a very important question. And also we're currently working with CAISO, and they are also very interested in this. And that also goes to your second question, that how will the future price become, and will battery try to exercise market power in that case. We actually did some very preliminary studies showing that if you, with this model, if the battery starts to bid, it actually, it eats up this profit pretty quickly, and it actually could make the battery profit negative, meaning that the price battery predicted is starting to become very different to the actual price. And then you're starting to have this loop that everybody try to predict price, and then their bids in turn sets the price. And yeah, it will be pretty interesting to know what will happen.
Yeah. Thank you very much, Volum.
So then we get to our last presentation in the session. It's on recent results of energy disaggregation by Meng Wang.
Okay, hold this. Thank you. Okay. This result is done by my student, Ming Yi, who is about to graduate, and a past student, Wenting Li, a previous student, Wenting Li, who is at Los Alamos National Lab, and collaborator, Dr. Yisheng Wang, when he was at JERENA. So the problem we want to address is that at the substation level, we only have the total power consumption. So that is the power consumption of all types of loads, like residential load, industrial load, and solar generation and renewable generation. So in this talk, I just refer solar as load as well, but it's actually an active load. So the problem we want to address is that after we get these total power consumption, can we separate them? So can we find the power consumption of each type of load separately? The reason we need this information is that we can use that for example, load forecasting, especially behind-the-meter solar, and we could use that for demand response and hosting capacity analysis. Now, compared with disaggregation at a substation level, the problem that is more widely studied is the load disaggregation at the household level. So similar objective at the household level, we have the total power consumption. We want to separate power consumption of individual electrical appliance in a household. So there's a lot of work there with different type of approaches. So there's some similarities with the problem we want to solve, but there are some technical difference. So first of all, at the household level, data temporal resolution is higher. Usually we could get one sample every few seconds. But at substation level, it's not as high sampling rate. We may get one sample every 5 to 15 minutes. And therefore, it's more challenging to identify the patterns at the substation level. And another advantage at household level is that we could find the historical data of each individual appliance. Therefore, we could use that information to learn the pattern of each individual appliance. That helps a lot in disaggregating data. So at the substation level, in addition to low temporal resolution, one problem we are facing here is that we might not have clean data for each individual type of load to estimate its patterns. So even if we have the recorded data for training, in that data, oftentimes the power consumption is the aggregation of multiple types of loads. And then that makes it more challenging to extract the features of individual types of load. And another challenge is that oftentimes we call it partial labels, which means that we don't know what are the loads that exist in this aggregated measurement. For example, like behind-the-meter solar, in certain time window, we might not know whether the solar is producing power or not. So therefore, the problem we are dealing with that even if we have recorded data, historical data for training, some of data include multiple types of loads, and we don't know we don't know accurately what are the loads that exist. For example, here, suppose this is the power consumption, total power consumption we observe. It is a summation of these 3 types of loads. And this is another example, total power consumption, summation of 2 loads. But this information might not be fully known to this operator. It may only know, let's say, load 3 exists, but load 1 and 2, whether they exist or not, it might not know. So that is a problem we want to address. Before I talk about our approach, I want to briefly mention about existing works. Existing works of disaggregation results in the substation level is much less than the ones on the household level. Oftentimes, some works use these load forecasting, use physical models, weather information to forecast solar. There are also data-driven approaches like dictionary learning approach, but still they need data, clean data for individual types of load to learn the patterns. So we want to drop this constraint in this work. So this is our problem formulation. So suppose we have total n types of loads, and we have, to simplify the problem, we consider a fixed window length m. And we have some recorded data for training. So we put these data into a matrix. Each column is the total power consumption in this m time step, and in one time window, and we have capital N of them. And you can see the total power consumption may include multiple loads. Let's say this one is a total consumption of load 1, 2, and this is one is total power consumption of load 1, 2, 3. So if I know, if I have knowledge of the ground truth label, I should know the label should be, this should be 1, 2, this is 1, 2, 3, and this is only 1. However, at the operator side, it might not have the full information because of partial label issue. So it may only know, let's say, load 1 exists in these 3 training samples, but not so sure about 2 and 3. And then the problem we want to address is, okay, now we have all these training data. We have these data matrix corresponding partial labels. Well, the objective is that now give a real-time measurement, let's say total power consumption in a time window length m. We want to decompose it into different time series that corresponds to different types of loads so that it adds up to the total power consumption. So this is the load disaggregation problem we want to solve. I'm going to first mention our deterministic approach that is essentially based on dictionary learning. Then we are going to talk about our follow-up work on Bayesian approach that can further provide an uncertainty characterization about our estimation result. So first we have these two, so we have offline stage. Offline stage is the training stage. So we have the recorded data, we have partial labels. We want to use that information to learn the patterns of individual types of load. And these patterns are summarized by this dictionary DI. So if you look at this as the training data we have, still every column is a time series measurement at one window. We want to decompose them into multiple matrices. Here, let's say 3 types of load, 3 matrices. Each one is the load consumption, power consumption of one node, and we want to write it as a decomposition of some patterns in the dictionary, multiply some coefficients. The coefficients is sparse, like mostly 0, because all the patterns might not appear simultaneously, but this dictionary collects all the patterns for one load. And then the objective of this training problem is to learn this dictionary D and the corresponding coefficients A so that they kind of add up to my total power consumption. So the first term here is just minimize the reconstruction error, like the typical dictionary learning problem. Now, to address the partial label problem, we add the second term, which is the column sparsity regularization. So the idea is follows. So in this example, suppose we know load 3 exists. Okay, we know it's clear, it's correct. Load 3 always exists in this training data, but we have no information about load 1 and 2. In this case, we are going to add column sparsity constraint regularization on these 2 loads. So the idea is that by doing so, we can accommodate the fact that load 1 and 2 could exist in this sum of training data, but we do not want to, but most likely they won't appear in all the cases. That is because if you have many loads and they have a large window, it's unlikely that this load will exist consistently. And then this sparsity L1 regularization promotes a sparse solution. And then third term is the incoherence term. We want to make sure the dictionary we learned for dictionary, a different type of load are as separate as possible because we need that kind of separation to do load disaggregation. Now combining all this is a non-convex optimization problem. So we have like an iterative procedure, update D and A iteratively and start with multiple initialization and pick the best one. Now, after solving the offline training stage, we know the dictionary patterns of each type of load. Then in the, this is just saying I include both load and the generation. Okay, so in the online stage, it's actually straightforward. So now I have a dictionary, I have total power consumption, I just need to solve this sparse decomposition problem to figure out the coefficients, then I can know the total power consumption of each type of load. Here we make one modification compared with standard method is that instead of directly disaggregating respect to the dictionary we learned, we want to disaggregate respect to the sparse coefficients we learned. The idea is that the patterns, power consumption patterns, may be repetitive in time. So we want to essentially view these power consumption we want to disaggregate as some patterns, some repetitive pattern that we can see in the training data. So by doing so, that can also simplify our computation and improve the accuracy. Now, this is some numerical evaluation. We have the ground truth data set. We pick solar and we pick 2 industrial sites together. And then the window is like 8 hours, 5-minute resolution. When we build the training data set, we put like gamma percentage of them that only include one type of load, while the remaining part are all aggregate load, including all kinds of combinations of aggregation. And then for training sample, we only have one label. So it's like even if it has multiple loads, 3 loads, we only provide the label of one load. So that's the partial label information. And then there's no label for testing data. So testing data, the objective is to disaggregate of the testing data. So here is comparison of our proposed approach compared with existing ones. These are different error metrics. The smaller the better. So you could see we indeed achieve a smaller error compared with existing ones. So the major reason the existing ones do not perform well is that they all rely on the clean data of individual type of loads, like I said. So they want to extract patterns from this clean data. Now, because our data have these aggregated, like aggregation from multiple loads, if we apply them, the patterns that they learn actually have some errors that leads to the high error here. Okay, so this seems to solving the problem, but there are some issues we want to further address. So first of all, this dictionary learning problem, deterministic dictionary learning problem, has the drawback that it is sensitive to the dictionary size, like how many patterns I pre-specify for each type of load. If it is too large, then I do not get distinctive pattern of different type of load, so I cannot disaggregate accurately. But if it's too small, I kind of miss the important patterns of a certain load. And that is not easy to determine. And another thing is that we don't know how reliable our results are. So this is I give you 2 cases. This is the total power consumption of possible 3 load as another case. And these are the disaggregation results against the ground truth. The ground truth is red, the green is our estimation. So you see, indeed, it's not always 100% accurate. Can be some errors. But how do we know whether these results are reliable or not? So to address this problem, we further propose this Bayesian approach. So still doing the same thing, I want to do dictionary learning. I want to separate the data into like multiplication of dictionary of coefficients. Now just instead of solving a deterministic problem, everything becomes probabilistic. Sure. I give a prior assumption of these dictionary and coefficients, and these training data just help me to estimate the posterior distribution. And the nice thing about getting this distribution is that now in testing stage for each data, instead of just get a deterministic result, I have a probability distribution. So what I'm going to do is that I'm going to use the predictive mean as the estimation of the disaggregation of each load, and I'm going to use the variance as an indicator of how reliable this result is. So intuitively, if the variance is very large, I will say this result is less reliable. To evaluate this, in addition to the traditional root mean square error, we also consider a weighted root mean square error. Essentially, just weight the error by this uncertainty. Intuition is that if this result we know has higher uncertainty, we'll essentially just ignore that part. And we are going to see whether this is improve the performance. So here are our results, still on the same setup, same data set. This is the Bayesian approach. This is the deterministic approach. First, in terms of error, it's less already improving. Interesting thing is that this weighted one is significantly less than the normal averaged one. So that is because, indeed, for those ones that has larger errors, we indeed have a high uncertainty index. And that index Therefore, it makes arrow smaller. But the key is not about the arrow. It indicates that our index indeed corresponds to the case that we have a larger arrow. So that could be used as evaluation about how reliable the result is. And also the performance is robust to the dictionary size. We can choose a very wide range of dictionary, and then we can actually prune it to the proper size. So in summary, so this is the two cases I showed earlier. Now, instead of just give you a point estimate, I can give you essentially a distribution. So I can give you a confidence interval as well. Now you can see these results are much closer to ground truth is mostly in this confidence interval. So in summary, the major problem we want to address here is that in the disaggregation at the substation level, we might not have clean data set for training, clean data set for individual type of loads for training. And then the major problem we want to address here is these partial labels, aggregating measurements of partial labels. And here we actually assume the label, although it's partial label, is accurate. So next direction we want to explore is what if this label information is actually inaccurate. Okay, thank you.
Yeah, thanks a lot. We take again one question from the audience. Okay, no question from the audience. Then quick question from me. So you showed in your numerical results that you had these PV units and the 2 industrial loads.
Right.
So I mean, this is kind of a small sample. You showcased how it would look like. What do you expect if you do this for larger sets, say on a city level, where you look at a couple of thousand households or industrial loads? What would you expect there?
Yeah, that's a good question. First of all, in terms of computational time, it indeed scales with the a total number of types of loads. Mm-hmm. So if for households, it's still considered as one residential load, so that aggregation one residential load. But indeed, I think it's in terms of cubic, in terms of total number of type of load. And in addition to the computational cost, I think is still solvable. It's not that time consuming actually. Another problem is that if we get more types of load, this aggregation result may become less accurate because they may have similar patterns, and for those similar patterns, you really cannot distinguish which one belongs to which.
Mm-hmm. Okay, good. Thank you very much. Then with that, we're actually perfectly on time now for 30 minutes of panel discussion. Spiros and I would like to invite now all the presenters and maybe some motivated co-authors as well to sit in the panel. And as we kind of came common in the last days, so if you have questions, so just, be in line with the microphone. So we already have a first question here.
Mihad Reza Shafiqa from University of Warsaw. I have one question, actually 2 questions. One question from related to the presentation of Anton, and following the question of Claudia, I have one concern about using your physics-based model for gathering the parameters of second life batteries, because as you know, the degradation and also the aging models of second life batteries are more important than the new ones. And I want to know that, is it possible, and which type of testing, which type of battery test or models is needed for getting the enough parameters for your model?
Okay, thank you very much for the question. So second-hand batteries. So first, they have different degradation mechanism. So if new batteries, they're more about solid electrolyte interface, which is layer which is growing because of side reaction.
Please closer to the microphone.
Electrode. But for the in case of second-hand batteries, close. Okay, so in case of second-hand batteries, there's a process, it's lithium plating, so it's more important for them. And it's also, there is physical description of this process, so it can be integrated in the model. But, so you have to start with a new model. And for this, with a new battery, you have to know the history, what happened to this battery, how it was operated, what was the, how much how many days the battery was in service. Then you can estimate what is the state of battery right now, and then from this point of life in the battery, you can use some physics-based description of the process which will happen to the battery. So, and again, returning to your question, you have to start from the beginning. So you have a new cell, you know these parameters of this cell, and then you can finish at the end, at the second stage of the life. You have to.
And how to get this digital twin model for the batteries? You need some extra battery tests, or just the histories of what happened before is enough?
So first of all, for the new battery, you need to know, for the new cell, you have to know the parameters. It's the dimensions of the cell and what's the chemistry of electrons. If you know this, next, you have to know how the battery was operated. So if you know this information, you can get to the state when the battery is it's reached 80% state, energy capacity. So it's decommissioned battery, and we move this battery to this second-hand usage of the battery. So, and parameters, okay,
Yeah, maybe we take that question for the lunch break. And so maybe some of the others on the panel would like to, comment. If not right immediately, then we would go to the next question from Ian.
Ian Huskins, University of Michigan, another battery question. So it's kind of my understanding, now I'm not a battery person, but batteries charge using this constant current, constant voltage regime, right? Most of the energy is delivered through constant current, but most of the time is taken up with the constant voltage part. So when I read papers and listen to talks about people using batteries, that doesn't ever seem to be built in any of the constraints. So are batteries really charged using CCCV, which I think is the case, and does that influence the physics, and should that be a constraint that's built into algorithms that are making use of batteries?
So for constant current, constant voltage, it's the fastest way how to charge the battery. So it's usually how the battery is charged in your cell phone or for consumers electronics. In the power system, in my case, when I was modeling my optimization framework, I assumed that my battery supply consume constant power. So I was not talking about the time how quickly I will charge my battery, but for me it was more important the stable level of charging and discharging during the 1 hour. So in this case, it's yes, of course, first is so because voltage and currents they change one change and they're interdependent. So it's how the model will decide in the optimization.
Okay.
Yeah, Bolon, please.
Yeah, probably just a quick add-on. Yeah, so following Anton's comment, yeah, so I think I think the question generalized to the dependency of power rating with respect to the state of charge, because the CCCV is that you don't want over voltage at the high SOC level. So in consumer electronics or electric vehicles, the BMS is relatively not as complicated for the grid battery, so it's more obvious. For grid-scale battery, it still exists. It's just that the nonlinearity or the dependency is not as strong as those in the cars. But on the other hand, we are doing some preliminary studies on incorporating this dependency, and we actually see of all the nonlinearity, efficiency, power rating, and degradation, the discharge power rating is actually the most significant one. Because if you think about how the battery make money, is that if you look at it, it's actually the majority of the point it tries to discharge when the price spike happens, right? And so the idea, so the name of the game is when the price spike happens, you want to discharge as much power as possible. and the price spike only lasts for 5 minutes. So you want to stay in the region where you can always shoot out the most power in that. So if you neglect that dependency, you may, for example, the battery was at 10% state of charge, at 90% state of charge, but in the region it cannot shoot the most power, it actually lost most profit. So I would say this is actually a pretty important topic, and I think recently, by recently I mean like over the last year, there's been a couple of papers coming out on this, and we're also doing some study on this. Yeah.
Okay, then I see Misha there, who was trying to ask for a long time questions, and now he's even there with his book. So, welcome, Misha.
Yeah, Ms. Chertkov, University of Arizona. Well, I have 3 questions, but I'll start, well, I'll limit it to probably Meng. Yeah, so very nice talk. You've been talking about disaggregation, but how about aggregation? And the balance between those two. So when we discuss aggregator, right, aggregator need to make decision on selecting those kind of units. We've been discussing aggregation in the context of TSL. Now there are batteries, there are many options, right? So how you view this, what you discussed as a disaggregation, can you use it as a guidance to aggregator later on? How you kind of balance between those two?
Actually, I should say that I haven't thought too much about aggregation. So for, I'm not sure you're talking about aggregation of the loads?
Yes, aggregation of loads. For, well, aggregator, well, small loads, right? So doesn't have much of a sense for individual load to participate in the market, but aggregator can do it on behalf of ensemble. So we had a lot of discussions, well, Ian and other on TSLs, right? So now extending those ideas and merging maybe with yours.
Right, so for this aggregation problem we are dealing with, the major, I would say major tool or technical things we could address is that we want to figure out the patterns or like features of individual type of load out of the total total load. And that feature may not be visible to the operator. That's what we want to figure out. But for your question, I'm just wondering if you still, that information of individual pattern will be useful to you, to the operator. If so, then maybe this kind of like dictionary learning or other approaches may be helpful to figure out the patterns first and then decide how to combine the patterns to make it total balance or something. Yeah, that's on top of my mind. Yeah.
Yeah, I had a comment. I hope you can hear me.
Yes.
You know, the aggregator bids in the ancillary service products market. So the aggregator understands what kind of a load flexibility it needs to bid for that product. They understand that. Now, when they go to the load to aggregate, they are not sure what exactly is going to happen with the resources that exist at the load because of all of the dynamics that are happening in the meantime. It's not something, you know, instantaneous. It's something you bid ahead of a time, and you don't know when you have to deliver what resource will actually be available. So I was discussing how you could, or you, meaning the aggregator, how they could communicate with the flexible load. Now, I was talking about very specific flexible load to tell the aggregator what is the flexibility that they can offer at the time of delivery. And I am, you know, I hate to do this, but because you cannot see it, but, you know, there's an app here with some circles and stuff like that, and Shmuel knows what I'm talking about. You know, I can monitor my load at home. Right now, it's, I don't know why it jumped to 5.7 kilowatt. It was 4 a minute ago. And I will be paying now 64 cents an hour. I was paying 48 a minute ago. And so I have a profile also of every second at my home right now, what loads are in and out. These circles are talking about the permanent loads and the loads that are coming on and off and stuff like that. So this technology exists, not that this particular product is the greatest product in the world, so don't get me wrong, there are better products than this. And Shmuel got me into this, so I wasted my money. There are better products than this, but that's okay. But it also tells you, the export, if you solar export. So my point being is this, that maybe we're not, realizing, we being, the community and maybe even utilities, that this characterization that is dynamic can be achieved. And then the aggregator, knowing what they are bidding for, only need to know what is the status of that resource, flexible resource, at the time when they need to go in. Because they're risking otherwise. If they don't deliver, they will be penalized basically on that. So that's a comment, I don't know, for whatever it's worth. Okay, so.
So I see Shmuel there, and then maybe again Misha.
Since he got me into the discussion, I made him buy this unit called Sense that is produced by Schweitzer. Well, the point is that a lot of the flexibility, when you talk about aggregator, it depends what you're talking about. What are the basic elements that you're going to aggregate? If you're talking about, for example, aggregating thousands of consumers like water heaters, you're talking about very small amounts like kilowatts. And the aggregator, all they really know is that they know the nameplate of the device at best, that they are going to try to curtail for limited periods of time through some technology that they're going to put behind the meter, the edge technology. So I think that when we talk about, there is the issue here that the aggregator, like under 2222, if we want the aggregator to operate like a virtual power plant and to actually offer some sort of a supply function, we have to recognize the uncertainty that the aggregator faces. The aggregator is going to interrupt customers at, large number of customers. They don't know if the customer was at home or not, or how much energy was actually being consumed at the time of the interruption. Even if they knew how much energy was consumed at time interruption, they still don't know how much would have been consumed once they do the curtailment. So you need some analytics, and you need to start to think about it as bidding some sort of resources under uncertainty. I've been advocating, for example, we have a project under ARPA-E that we start to use technology, methodology that have been used in the revenue management industry, a methodology like newsboy problems, where you're bidding uncertain resources and you have to commit to a certain amount, and then you have to use some analytics that is, because you get paid for how much you commit, but you pay for how much capacity you are curtailing. And you have to maximize the revenue, and so there are methodologies for managing the risk of delivery that the aggregator have to adopt in order to, when they do this kind of, bidding, because they commit, let's say, to PJM that they are going to deliver so many megawatts, or megawatt hours, and there is a lot of uncertainty around them, and to be considered as a legitimate generator, they have to somehow manage that risk. So we have to start to adopt methodologies that have been used for hedging, financial hedging, and managing the risk.
Okay, thanks for that elaborate comment. I see Maria Illich there, who would like to follow up. Please go ahead.
Maria Illich, MIT. I think this is primarily for you, Bolan. At the beginning of the talk, you said there is a large growth of batteries, but then you were concerned about them going out of business after a while. So I think there is this hidden question of what would be some reasonable amount of batteries to invest in so that they can be competitive with some maybe more conventional technologies, with software and so forth. I think it's a question that cannot be avoided, because otherwise we are going to have a lot of sunk cost and things like that. We've seen that with Flywheel, Satcon went out of business and ancillary service in New England, and the story keeps repeating. And so we cannot just take biased technology approach. So I think what Jan said about not just assuming that we are all price takers and not closing the loop, it's extremely important. I just want to mention at the expense of advertising my own work, the Diamonds framework really does not take this type of bidding as price taking. It closes the loop, and system operator gives the sort of an online setting some information about what's going to happen in terms of prices and so forth. So I guess the question at the end is, how do we connect the operational benefits from storage with the investment decisions? I was wondering if you can comment a little bit on that.
Okay, who would like? Bolon?
Oh, yeah. Thanks, Maria, for the question. Yeah, I think this is an issue that even the system operator, like I've been talking to this guy in Kaiso, and he also doesn't know what will happen, because I think really the question is better is not bidding physical cost, but everybody is trying to predict the price. So it is a loop, but it's a loop that nobody knows where it goes. So at least for the current market, if we're only looking at incremental changes, we only can try to design more better bidding models that kind of try to navigate more of the storage into align with the the social welfare. But then the question is, how could we better coordinate these batteries so they don't fight with each other? Should system operator publish price forecast? There's a lot of stakeholders in California asking Kaiso to publish their price forecast because they are using price forecast to do this look-ahead dispatch, but they are not publishing that. So that's one question. But on the other hand, I guess to the investment perspective, the good thing with batteries is even if they do not participate in the market, there's also other like resiliency services you can provide. So there's more like a stackable value. So I think that will be also one of the good benefit for batteries in this market.
According to recent data and what Bolon showed, the duration has changed. Like before, the majority of storage was 1 hour, like lithium battery. Now, it's more about 4 hours. So it's a huge, 4 hours means storage participates in the energy arbitrage. And because we have more renewable, the price volatility, and if you see on the price volatility in different markets, it's increasing. Because of more integration of the renewable, volatility of prices is higher. And higher volatility of prices makes, like, it's where the energy storage will make money. So I think, like, the ancillary service market at certain point, yes, it will be saturated, and better energy storage will move to the energy trading. And I think it's happening now.
Thank you. Okay, then Misha was waiting for a long time. You have a second question.
No, I can hold it, but it's actually a question, about batteries. I think mainly to Anton, but probably to Bolon too. This balance between physics and markets, right? At least those two aspects. And so you obviously guys manage it. In Bolon case, it's very simple model, right? In Anton case, it was first rather evolved, right? PDs, and then all of a sudden you jump to oversimplified model motivated by market or by physics, and that was not clear to me, because if it is motivated by physics or chemistry, you need to tell us what are small parameters or physical arguments about linearization. I didn't hear that. Maybe, well, you probably have it. So if you can clarify that. But in general, question is how we kind of manage it. In other devices, like thermostatic control load, yes, we use oversimplified models, but they're much simpler devices. So battery seems to be much richer, and what is the right balance to use an economic model? It's completely not clear to me.
So, first of all, why now a lot of modelers use simple model? because usually what I see from the experiment data we had, the manufacturers of lithium-ion battery storage, like these big containers, they overbuilt their storage. So usually the storage operates in the linear range. And so, so it should be good using for the operation, but not for predicting degradation. I think in my model, this is why our evolution of the model, we started from the physics-based model. And we can see the results of the experiment with the Tesla Powerwall, that we don't see non-linearities over there. But why we need this physics-based model? Physics-based model will help us to model physics-based degradation. And this is more important. Not like this, when we overbuild the system, okay, we can use the linear approximation. But for the description of the degradation, it's better, according to what results we received, physics-based degradation description plays an important role.
If I can jump, from what I heard, it's outdated. This degradation, so I actually discussed it with chemistry, physics experts a couple of years ago. And back then, main trouble was that they really don't have experiment, right? Because we are talking about, I don't know, years ahead, and those batteries are renewed every year, right? So technology changes fast, and it was not clear how you can possibly experiment with that, how you model this. There was a lot of questions. So now you are telling me that the detailed model already exists, which allows you to predict in the future. But on the other hand, you immediately linearize it in, not clear fashion, right? So how do we balance all of that?
Let's start with linearization. So the linearization, there is in the paper, you can, this conference paper, you can see the steps we did and what the justification from the electrochemistry people we did for the simplification first. So the other thing, we use a digital twin. So we don't do, for comparison. So we have our system without any simplification, and we put our dispatch in this true model to see what will be the output and compare this output with what we receive from our linearized model for comparison. And for parameters, yes, you're right. So, there is not many experimental data on particular cells. So it's just lithium cell community people, they create database where you can get access to these parameters.
So let's take it.
And chemistry, right now the chemistry is just limited for the electrodes. For negative we're using carbon with some additives, and for positive electrode we use three types of electrode: NMC, NCA, and LFP. And for this one we have they measured parameters for electrochemical model are known.
So let's leave it at that for now. There's opportunity at lunch and dinner. Sakis Miliopoulos was waiting for a long time. Please go ahead.
Thank you. I have a couple of questions for the second paper for Ilgiz. The concept of incorporating intractable constraints into optimization and artificial intelligence is excellent. You have an example of including small signal stability. One question is, I assume you used legacy system, a synchronous machine type system for the small signal stability constraints. The question is the following thing, that is, if we go to the present system with a lot of inverters and so on, then obviously the controllers of the inverters are determining a lot of the small signal stability of the system, and we run into the size of the problem is a little bit much bigger than the legacy system. And since you are converting into MILP first and then you you apply the method. What are the implications of this? How the neural network will work when we have a huge MILP program? So that's one question, and I have another question. And the other question is the following. Your idea of shrinking the solution space so that you avoid the edges where you may have an infeasible solution, it's an excellent solution, but since we have a good method to incorporate intractable constraints, how about after the solution to define more constraints that will limit the solution space to go into the infeasible system and use the same method to compute the solution?
Yes, thank you for the question. Yes, regarding the first one, where we have...
Yes, okay. So regarding the first question, when we have like a lot of inverters, so here the thing is like how big neural network we need at the end to capture all this feasible space. Of course, like the bigger network we have and the more kind of equipment we have, so I expect that the depth of the neural network will increase, and that actually what will influence the size of this milk problem. Regarding the second question, I haven't think about this. We haven't think about this, but it's I think it's something to check actually. So instead of resolving it again, maybe we really could just include as a constraint directly.
Thanks.
All right, then one last question.
I have a very quick question about the disaggregation and aggregation. Actually, based on analyzing the data of the behind the meters, have you considered the privacy of the customers? For example, when you disaggregate your data from someone coming from Finland, I can understand that in some hours which are of the loads, there's a kid alone at home. How do you contact this problem, and how do you consider this from the viewpoint of the aggregator?
Oh, sorry, may I ask the question again? What's the question?
I like to know that, is there any way to have the privacy of the customers when you are going to analyze the data behind the meters of them? And because many of the places, many of the countries, they don't like even having any aggregator. They prefer some types of decentralized form or any other types of the market, not having the aggregator or any entities to have to actually extract the data from them. Could you please comment on it?
So for this problem, I can think for us, we only consider like if we have the total information, total power consumption, what can we get out of it? And then if you're asking like after we get this information, what they can do about it, then I would think they could try to see if they are trying to meet certain kind of total demand, then can try to aggregate them together with different combination and see whether it meets the criteria. I'm not sure if I'm answering your question.
So before getting any data, you already get a kind of contract or the confirmation from the owners of the home, the customers, that we are using all the data and.
So I think for us, we are not having the talking with any individual household. We just look at one particular substation, what is the total power consumption. And for the residential load, we are estimating it is the total power consumption of all the residential loads. We are looking at in total, what will be the total aggregation pattern in this under this substation? So I'm not talking with individual household like to share with me like their power power information. And so and then so the patterns we learn will be an aggregated behavior. Then if there may be an aggregator there that may affect the behavior, that may be. But for us, we just observe what will be the net behavior of these individual households.
So you're only considered a kind of a clustered weight of the loads.
Exactly,
so
yes.
No violating the privacy. Thank you.
Yes,
okay. Great. Then time is up. Thanks again to the panelists. The session is adjourned. Do enjoy your lunch, and then we see each other for session 14 after lunch.